Today we're going to be talking about compound interest. Okay. Now this is one of the IGCSE extended topics that you have got to be quite comfortable with. The reason behind that is because it mixes several skills. In particular, it mixes geometric sequences and logarithms, okay? Both of which in extended IGCSE you need to be relatively comfortable with. Now the idea with interest rate questions is usually quite similar. You know, that there are some twists and turns here and there, but at the heart of these questions, the essence is always the same. So the deal is today, I want to make sure that you take a couple of notes. There's a formula in particular that I'm going to give you in just a minute that you have got to make a note of. It's extremely important. And we're going to be working with that formula throughout this class, okay? So, first of all, I'll read this question. You may have read it already. This first question tells us that Clara puts 2,000 euros in her savings account with compound interest, that's a very important term, compound interest, at an annual rate of 4%. We're asked two things. Question A, how much will she have after 3 years? And question B, how many years will it take for her savings to reach 15,000 euros? Now, I'll break the suspense right away. We're going to be using logarithms for answering any questions looking like this question B. In other words, as soon as we're asked how long will it take, anything like that, we're going to be using logarithms for this type of question, okay? With that said, let me start by answering question A, of course, and for that, I will give you the formula that you have got to write down, okay? Now, let's say I'm investing money, like Clara is here. She's putting 2,000 euros in her savings account. I'll call that initial amount that we start off with, I'll just call it P. So I'll go ahead and say, okay, I'm investing P. And I'm interested in knowing how much money or what amount of money we'll have after N years. So I'll just say A is the amount that we're going to be calculating, okay, and that's after N years. Well, the amount we'll have after N years will always be given by this formula. It's P times, in parentheses, 1 plus R over N, close parentheses, all of which is being raised to the power of N times T. Don't worry, I'm going to explain what each of those is in just a second. I'm just going to box that result. There we go. Boxing it. That formula is what you have got to make a note of. Okay. Now, let's be clear. I'll write what each of these is in green on the side here. A is the amount we have, or I'll just say amount after N years. Okay. R is the interest, or I'll just say it's the rate, which is why we chose the letter R, expressed as a decimal. Okay. And N is the number of years. Okay. And actually, my apologies, I'm being very silly. N is not the number of years. N is the number of time. Don't worry, that's going to make sense very shortly. And T is time in years. Okay? Now, take a few seconds to write that down. Okay, that's extremely important. That formula is going to follow you throughout high school. Okay, as soon as you're going to be dealing with interest rates or anything like that, or even exponential decay, it's going to be extremely similar, with the exception that you'll have a minus in the middle here. But as soon as we're dealing with exponential growth, we'll deal with this. As soon as we're dealing with exponential decay, we'll be dealing with this, with a minus in the middle. Okay, so do make a note of that. Really important. Now, so to be clear, P, and actually I could write P as well. I should, shouldn't I? If I write P at the top here, P is amount we start with. Okay, there we go. So, to be clear, A is the amount of money we'll have after T years. P is the amount we started with. So in this example here, P would be 2,000. That's how much Clara initially put into her savings account. R is the rate, and the rate will always be an annual rate, don't worry. So in this case, it's going to be 4%. N is the number of times interest is applied in a year. We'll get back to that in a second. And T is the time in years. So T is going to be 1, 2, 3, 4, etc. Number of years. Okay. So let's see. I'll go ahead and actually illustrate how we use this formula by answering question A. We're asked, how much will she have after 3 years? Okay. Well, let's see. Given that this is a compound interest problem, we're told in the question compound interest with an annual rate of 4%, we know that this is the formula we have to use. Well, to answer this, question A, since we know that it's compound interest, we know right away this is the formula we have to use. Therefore, we can just go right ahead and state that we're going to use it, and we can just sort of quickly look at the formula and figure out what P would have to be, what R would have to be, what N and T will have to be. Okay. So the initial amount she starts with is 2,000. So that allows me to write, okay, well, P is equal to 2,000. Okay, and I do that just reading through the question. Next, I'm looking at R, that's the annual interest rate. And again, we're given that in the question, that's 4%. So I can just write that at the top. Okay, R is equal to 4%. But notice that in the question here, or rather in this formula, I clearly stated that the rate has to be expressed as a decimal. I'm quite certain you're all comfortable with the idea of me writing 4% is equal to 0.04. Okay, that 0.04 is what I want you to work with this formula. All right. T is the time in years. So we're interested in how much you'll have after 3 years. So T is going to be equal to 3. So I just write that as well. T is equal to 3. And now N. N. Well, let's see. N, like I said in the description at the top here, N is the number of times interest is applied in a year. Well, to make things simple for this first example, I haven't specified much at all. I've just said there's an annual rate of 4%. When that happens, you can go right ahead and assume, okay, this interest is applied once a year. So let's say she opened up her account in April, then at the end of April next year, interest will be applied to her savings, okay? That's the idea. And I want to say in the real world. So we can say, all right, well, the amount Clara will have after 3 years will be A, which is going to equal to 2,000, times, in parentheses, 1 plus R. Remember, R is expressed as a decimal, so it's 0.04 over N, which is 1, and all of that's being raised to the power of N times T. So that's going to be 1 times 3. We can tidy that up, of course, and state that that's equal to 2,000 times 1 plus, well, 0.04 divided by 1 is just 0.04. So 0.04 raised to the power of 1 times 3, which is 3. Finally, simplifying what's inside this pair of parentheses, we quickly see that the amount Clara will have after 3 years will be 2,000 times 1.04 raised to the power of 3. Now, the good news is this type of question is always going to be a calculator question, unless you're allowed to stop there. But if not, it will definitely be a calculator question. And so at this stage, you dive onto your calculator, and I'll just make mine appear here. Let me see. I've got my calculator, which I've hidden, and now it should appear. And in fact, for the sake of leaving as much of that formula at the top as I can, I'll sort of try and make it fit right there. Okay, and I'll extend it a little bit. There we go. Now, with my calculator, I go ahead and calculate this. So let's see. If I go to a scratch pad and I calculate, I need to calculate 2,000 times, in parentheses, so I'm copying exactly what I see, 1.04, all of which is raised to the power of 3. I type enter, and that's the amount. So after 3 years, Clara should have, let's see, A equals to 2,249.73. and that, of course, is in euros. And I'll box that result. Okay, that's how much she would have saved after 3 years. Okay, good. Now, let me hide the calculator for a second. There we go. If I go back to question B here, and I'll need a bit of space here, so I'll write that at the top. Question B, we're asked, how many years will it take for her savings to reach 15,000 euros? Now, in other words, if you just try and picture it, you've dropped off 2,000 euros in a savings account. You do not touch it, of course. You just let it grow, thanks to exponential growth. How long at this rate will her savings account have 15,000 euros inside it? Well, let's see. We're going to do this algebraically, without just throwing it in the calculator and looking at the table or looking at a graph. We're really just going to use, logarithms here. And the key thing to realize is that in this case, if I'm going to be interested in the amount after, I'll just say in a sort of generic, the amount she'll have after t years, because the number of years is the unknown here, right? And remember, t is the number of years inside this formula. So at this stage, what I'm going to do, my first step is I'm basically going to copy this formula. I'll replace p by 2,000, I'll replace r by 0.04, I'll replace n by 1 right here and here, and I'll leave t as it is, because I don't know what t is yet, right? That's what we're trying to find in the question. So that would be this. I'll have a equals to 2,000 times 1 plus 0.04 over 1, all of which is raised to the power of 1 times t. Simplifying that a bit, that's equal to 2,000 times 1 plus 0.04 raised to the power of t. We hopefully quickly see that's equal to 2,000 times, in parentheses, 1.04 raised to the power of t. And so that's the amount Clara will have after t years. And in fact, I'll go ahead and box that sort of intermediate result there, because that really is, if you were to plot this curve inside your calculator, that's exactly what you would plot, right? The only difference is, rather than using t, you would use x, and then you would actually be able to see the sort of exponential growth curve, all right? Now, what we're trying to answer in this particular question, and actually before I say that, it is worth pointing out, if you look at the result we just have, 2,000 times 1.04 raised to the power of t, and just compare it to the penultimate, or the line before last in our previous working, these are pretty much the same thing. I didn't need to do all this working again. I could have just read it off here, where I raised it to the power of 3 and just replaced this 3 by t. Right? Hopefully you can see that all these steps in my working are identical. The only difference is, in this case, I don't know what t is, but all the rest will be the same. Okay? So do keep that in mind, because it'll save us time. Now, what we're trying to figure out here is, when will her savings be basically greater than or equal to 15,000? Well, to answer that question, we're going to turn this question into an inequality. Okay? In other words, what we're really trying to figure out here is, when will 2,000 times 1.04 times t be greater than or equal to 15,000? Yep. That's what we're trying to solve. Now we can do that. Okay, we can go ahead and actually sort of rearrange this a bit. And in doing so, the first thing I'll do is, just as we did in the previous lessons, we're going to isolate this 1.04, which is raised to the power of t. In other words, we're raising the, how would I put this, the exponential term, right? Because once we've done that, remember, as soon as we have something raised to a power of x or to the power of t or anything like that, then we can apply our logarithms, and it's going to become easy. So let's go ahead. If I divide both sides of this inequality by 2,000, it's going to become 1.04 raised to the power of t greater than or equal to 15,000 divided by 2,000. Now you may see right away that's the same thing as 15 over 2. In other words, I'm taking a whole factor of 1,000 out, and that's equal to 7.5. Right? So in essence, what we're really trying to figure out here is when will 1.04 raised to the power of t be greater than or equal to 7.5, right? And at this stage, this is now, if I box that for a second, this is a typical logarithm problem. If I apply logs to both sides of this, I'll be able to extract the exponent t. Here's what I mean. I'll go ahead and just apply log, and again, as we did in our previous classes, I'm going to work in base 10, and I'll remind you of why I always do that with the calculator in just a minute. But if I write, okay, log base 10 of 1.04 raised to the power of t is greater than or equal to log base 10 of 7.5. Now I use the third law of logarithms that we've seen several times now. I'll write it at the top of the page though. Remember that if we have log of any base b of a number a raised to a power of x, then that's equal to x times log base b of that same number a. Okay? In other words, this really is the logarithm rule that allows us to extract the power and write it in front of the logarithm. And that's exactly what we want here, because we want to know what this t is here. In fact, to make that clear, I'll rewrite this and I'll put the t inside that pair of parentheses because it looks a bit ambiguous there. Okay? So, using this law, I can now write this inequality as t times log base 10 of 1.04 is greater than or equal to log base 10 of 7.5. Yep. Now, all I have to do is divide both sides of this inequality by log base 10 of 1.04, and that tells me that t has to be greater than or equal to log base 10 of 7.5 over log base 10 of 1.04. Okay? Now, that's all the algebra, right? We've gotten all the algebra out of the way. So at this stage, all we really have to do is just leap on our calculators, okay? And calculate what this ratio on the right-hand side is actually equal to. So let's go ahead. I'll make my calculator reappear, and I'll try and place it in the upper right-hand corner of the screen. If I just make it appear there it is. And if I move it to the top, like so, here's the idea. Here's why I like working in, how do I put this? Why I like working with log base 10 so much with this specific calculator. Okay. Rather than, we've seen how to access the log, right? If you press Control, I'll point towards it here. If I press Control, then 10 to the power of x, then I'll get the log. I then have to enter the base on the calculator. I then enter the input value, and so on. Which is fine. That works perfectly well. But this calculator, by default, if I just go ahead and type log, so I go L, O, and G, of course, and I'll just find the G, there we go, log, open up a pair of parentheses, and I write 7.5. Notice that I haven't specified a base here. And I divide that by log, so that's L-O-G again, of 1.04, and I type enter. The calculator automatically, by default, assumes that if you're not specifying a base, you're working in base 10. Okay? So that's kind of why I like to always just say base 10, because it just allows me to quickly type log with the calculator, and I have basically less manipulations to do with that calculator. Right? Now, we have the result on the screen there, and you can see right away, hopefully, that it takes quite a long time to get from 2,000 euros to 15,000 euros at an annual rate of 4%, right? So if I just copy that and I'll round it to say I'll round it to 1 decimal place, that's equal to 51.4 years, okay? Which is a little long, so I'll just underline that result, okay? That's how long it would actually take. Now, of course, in the real world, you don't just put 2,000 euros at the start and wait. You will add money, say, every month or every year at whatever interval you need. But essentially, that's how you're going to build up some capital or build up a proper amount of savings. But nonetheless, if she had just put 2,000 aside and waited along for 51.4 years, she would have 15,000 euros, right? Now, the point of this exercise is for you to see really where these logarithms become useful, okay? And with a calculator, you could solve this, of course, but some of you have seen, and I remember when we did this together in class, the 15,000, when you plug it in your calculator, was a bit of a struggle at times, okay? Because suddenly you're dealing with a scale on your XY grid, which is massive. And I remember when we did it a few times, a lot of time was spent actually really just calibrating the calculator window properly to be able to actually see the curve being this one here. And by all means, give it a shot. You can try that. And if you do, you'll get full marks in the exam, by the way. But I would strongly advise you, and this is particularly with IB in mind, to get used to working with the logarithms that I just did here. Okay. With that said, I'll go ahead and move to the next question. And I'll just hide my calculator first. Where is it? There it is. Hide the calculator. There we go. And I'll move to the next page. Okay. Now, in this example, we're told Charlotte puts 2,000 euros aside in her savings account, and it's compounded quarterly at an annual rate of 4%. We're again asked exactly the same questions. A, how much will she have after 3 years? And B, how many years will it take before her savings reach 15,000 euros? Well, the key distinction to make between this question and the one we just saw is the fact that in this case, we're told that it's compounded quarterly, and I'll actually underline quarterly twice. The difference that makes is the number of times per year interest is applied to her savings, okay? And it makes a difference. I'll tell you now, the difference when you're investing 2,000 euros isn't massive. For larger amounts of money, though, it makes a tremendous amount of difference. So, I'll just remind you of the formula at the top. Remember the formula to figure out how the amount saved after T years was this. A is equal to P times 1 plus R over N times, close parentheses, not times, raised to the power of N times T. And again, I'll go ahead and box that result. Okay? For the sake of reminding you, P is the initial amount that's put in the savings account. R is the interest rate expressed as a decimal. N is the number of times interest is applied. And T are the number of years that go by. Okay, so T is time in years. Now, with that said, if I now answer the questions, so I'll go through these. For question A, how much will she have after 3 years? Well, again, this is now that I've established that it's compound interest, this is the formula. So all I have to do really is replace everything I can inside this formula by what I'm given in the question, and as well as what I'm given in question A, so 3 years. So let's see. The amount is, again, I'll just summarize everything. The amount she starts with, so P is equal to 2,000. The annual rate, R, is 4%, which remember, express it as a decimal, will be 0.04. The number of times interest is applied. Well, this term here, quarterly, it's important. The IGCSE, or actually any examination board between IGCSE or IB, they're going to assume that you know what that means. Okay? Put simply, it means that interest is applied to your account every trimester, meaning every 3 months. Okay, so interest is applied 4 times a year. So in this instance, when we say compounded quarterly, it means that N is equal to 4. Okay? T is time in years. Fine, we'll get to that in a second. We're interested in how much she will have after 3 years. So in this case, T will be equal to 3. Yep. Okay, we have everything we need to calculate now. And we can just go ahead and say, all right, well, the amount after 3 years will be A, which equals to 2,000 times, in parentheses, 1 plus R over N. So in this case, that's still 0.04, but N is equal to 4. So I write that on the denominator. I close the parentheses, and that's raised to the power of N times T. Okay, so this time, that's going to be 4 times 3. Okay. Now, got to tidy this up a bit. Don't leave it like this, okay? Taking care of what's inside the parentheses, that becomes 2,000 times, in parentheses, 1 plus 0.04 divided by 4 will be 0.01. I close parentheses, and 4 times 3 is 12, so that's the power. I carry on. I quickly find that A is equal to 2,000 times 1.01 raised to the power of 12. And that's how much money will be aside, or will be saved, after 3 years. Again, you're not expected to calculate 1.01 raised to the power of 12 by hand. So we use our calculator. And again, I'll just make my calculator appear again. So let me see if I just make that appear there. Let's see, we are calculating, if I plug in all the numbers correctly, we have 2,000 times, in parentheses, 1.01, whoops, 1.01, there it is, raised to the power of 12, and I type enter, and we're getting, if I copy that correctly, it's rather small on my screen there, that's 2,253.65, okay? And again, I'll underline that, and those would be euros, right? Now, before I answer question B, let's just quickly compare that amount to what Clara had saved up with an annual rate which was compounded once a year. So let's see, if I quickly flick back, Clara had, I'll round it to the nearest euro, Clara had 2,250, and I'm rounding to the nearest euro, 2,250. Charlotte's getting 2,254 to the nearest euro. Again, not much difference, but there is a difference, okay? Now, that being said, I'll move on to question B. And again, I'll just write that at the top here. I'll just write that here. There we go. Now, for question B, we still have to answer the question, how many years will it take before her savings reach 15,000 euros? Well, okay, the approach is going to be the same. I start from this formula, and I'm going to simplify everything as much as I can, but, meaning I'll replace P by 2,000, I'll replace R by 0.04, I'll replace N by 4, though, and I don't know what T is, because that's the unknown we're trying to figure out. Now, like I said in the previous example, we could, of course, plug everything in and do all the algebra again, but the reality is it's more or less going to be identical. Right? Everything inside these parentheses will be identical, no doubt about it, because there's no T in there, right? There's no T inside this pair of parentheses. The only difference will be the exponent, and instead of being 12, or 12 here, the exponent is going to be N times T. Since N is 4, the exponent will be 4T. So to save us a bit of time, I'll go right ahead and say that the amount Charlotte will have after T years will be A, which equals to 2,000 times 1.01 raised to the power of 4t. Okay, that's our formula. That's our formula for calculating how much money she has aside after t years. Now, to answer question B, what we're trying to figure out is when will this amount be greater than or equal to 15,000? Okay, well, let's see. All that really means is we need to write an inequality. Okay, and so if I do that, what I'm trying to solve here is 2,000 times 1.01 raised to the power of 4t has to be greater than or equal to 15,000. Yep. Okay. So let's start tidying this up. I mean, this is, basically an exponential inequality, And so the first thing we really have to do here is isolate this 1.01 to the power of 4t. When I say isolate, I mean let's make it this, the only thing left on the left-hand side. For that, I'm going to divide both sides by this 2,000 that's multiplying it. So let's go ahead. That would be, I don't actually need those parentheses anymore, 1.01 raised to the power of 4t greater than or equal to 15,000 divided by 2,000. Just as in the previous example, we can of course simplify that fraction. You can start by saying that's the same thing as 15 over 2 again, and 15 divided by 2, well, that's 7.5, right? So the inequality we're really trying to solve here is 1.01 raised to the power of 4t, which has to be greater than or equal to 7.5. Okay? And now we're kind of set. Okay? We've reduced the problem, if you think about it, rather massively. Okay? We went from all this stuff over here to basically, a much simpler exponential inequality to solve. All we have to do here is apply logarithms, right? So I'll go ahead and I'll apply log base 10, right? As always, I stick to that. And because it's base 10, this time I won't even bother writing the base. Remember, when I don't write the base, assume it's base 10. So I go ahead and just say, okay, well, log of 1.01 raised to the power of 4t has to be greater than or equal to log of 7.5. I use the power rule for logarithms. Remember, I can take this 4t outside from the exponent position and place it as something multiplying this. And that would be 4t times log of 1.01, and that's greater than or equal to log of 7.5. Yeah. Finally, actually I could do it in two steps, I guess. I'll start by dividing both sides by log of 1.01. So that turns into 4t greater than or equal to log of 7.5 over log of 1.01. And finally, I divide both sides by 4. Now remember what I said, I believe it was a class or two ago. When we're dividing by 4, just think of it as multiplying by 1 over 4, particularly for things like this. As soon as you're dividing a fraction by 4, think of it as multiplying that same fraction by 1 over 4. When you do so, it turns into this. T is greater than or equal to log of 7.5 over 4 times log of 1.01. Okay? Now, calculator. So let's go. If I grab the calculator and I type the right-hand side here, let's see. I want to type all of this right-hand side inside my calculator. So if I do that, just put this pencil aside. So remember, with this calculator, if you just type log, it's going to assume you're dealing with base 10. So let's just do that. So log of 7.5 divided by, in parentheses this time, because I've got a number multiplying the logarithm, so make sure to write that in parentheses, 4 times log of 1.01. Exit all those parentheses and type enter. And in this case, what are we getting? We're getting, I'll round it to 2 decimal places again, so in this case it's 50.62. Now remember, those are years. So in Charlotte's case, for her initial 2,000 euros to turn into 15,000 euros, it's going to take, if I round to the nearest year, 51 years. In fact, I'll just write that underneath. I'll just say 51 years, right? Let's just switch, flick back to the previous page before I let you go to see how many years it was with Clara's bank. Let's see. If I flick back here, we had 51.4 years. So I guess if we round to the nearest year, it's more or less the same, right? But hopefully you can appreciate that if I don't round, 51.4, this 51.4 here is definitely bigger than 50.62. what that shows us is that with Charlotte's bank and the deal that they're offering her, her money or her savings is growing faster than Clara's. Okay? And that's always going to be the case. In other words, the number of times the interest is applied per year will have a direct, or will have a real impact on the speed at which your interest grows, or the speed at which, that sentence. A direct result on the speed at which your savings grow. Okay, that's important. And on that note, I'm going to leave you, but I'm going to ask you to work through during the next period. Okay, so I've taken over 10 minutes of your break right now. Next period, I want you to work through the following problem. Okay, I'll just read it out loud before I let you go. We're told that Benjamin puts 2,000 euros in his savings account, compounded monthly at an annual rate of 4%. How much will he have after 3 years? How long will it take for his savings to reach 15,000 euros? In other words, as you can see, same question again, but in this case, I want you to, well, first of all, realize that we're dealing with something that's compounded monthly. So ask yourself, how many times in a year is interest going to be applied? I'm quite certain you can tell it's going to be 12. So with that 12 in mind, use the formula and quickly calculate, or rather, quickly answer these two questions. Okay? That's all I want you to do during the next period. Make a good note of what you've seen in this tutorial or this video. Make a note of the formula. Watch it again if needs be, and work through this specific example or this exercise. Okay? We'll start our next class. That will be next week. Yep. Next class, we'll start by correcting this question. Okay? So you don't have to send the work back to me, but I'll start the next one, the next live session, correcting this. Okay, everyone? Anyway, I really hope that helped, and I'll see you next week, everyone. Take care.